Greetings. This tutorial shows how to make a replica of the 6 degree of freedom Euler angles block available in SimuLink aerospace blockset into the SciLab xCos development environment. Aerospace blockset is not implemented in xCos. A workaround might be to reproduce the block according to information provided by MathWorks in help pages. All superblocks used in xCos model have been tested with SimuLink counterparts. At the end of the video, you shall see that the obtained results are quite accurate. The results are validated by a model of 6 degrees of freedom motion platform, also available in SimuLink help pages. The block is thoroughly described in following MATLAB help page, including description of input-output ports and summary of ordinary differential equations used to do calculations. The system ODEs implemented in the block describes linear and angular momentum conservation in body reference frame and the relationship between the body fixed angular velocity vector and the rate of change of the Euler angles as well. To start using the block, some prior information is required, such as body mass and inertia tensor, assumed constant initial values of position and linear velocity, Euler angles, and body rotation rates. The xCos model is self-explanatory at top level. External forces and torques acting upon the mechanical system are fed to the main superblock. The force components are held constant while the torque components represent a train of rectangular pulses identical to those used in the SimuLink model. The superblock output comprises ports of linear and angular velocities in body reference frame, Euler angles and directional cosine matrix, position and velocity in inertial reference frame. Output information is further processed by user-defined functions, used to convert radians to degrees or keep an angle values within the negative pi to positive pi interval. Let's reveal the superblock contents by double-clicking on it. The block diagram may seem daunting and excessively complex at first sight. What you see on the screen is actually the block diagram equivalent of the ODE systems shown in the SimuLink help page. The equations are reordered so that only the derivatives remain on the left side. For example, at the top you may see a cross product, function ROT, between angular rates and linear velocities vectors. The product, also a vector, is then subtracted from the external forces vector, and the result is further integrated by 1 over s blocks to get the linear velocities vector and body reference frame. Remember, the 1 per s expression stands for an operator form of integral after taking the Laplace transformation. At middle of the diagram, the right-hand sides of the angular momentum conservation equations is shown. One user-defined function is used here to keep the diagram as simple as possible. The ROT function implements a cross product as already stated. Finally, the intermediate vector is integrated to get angular velocities rates and body reference frame. Thereunder, a diagram for determining the rate of change of the Euler angles is shown in terms of body-fixed angular rates. The user-defined function gimbal simply performs matrix times vector product according to the equations shown in the SimuLink help page. The directional cosine matrix is computed afterwards in terms of quaternions. A recipe on how to do this might be found in reference sources, precisely the Zipfels textbook, Modeling and Simulation of Aerospace Vehicle Dynamics, in page 127. Nothing to worry about. The computations actually are quite simple. Given Euler angles, formulae 4.78 is used to convert to quaternions, and then equation 4.80 is used to advance towards computing the directional cosine matrix. User-defined function Zipfel does this for us exactly. Last but not the least, position and linear velocity vectors are needed in inertial reference frame. It takes a matrix times vector product only to compute the velocity. To get the position, integration is necessary. An important question is how to set the initial conditions. Mass equal to 1, inertia tensor and tensor inverse are set constant. The initial conditions of integration are set by clicking on each 1 per second block separately. For example, the initial yaw angle is set to 0 in this case. To set up simulation time in xCos, go to Simulation/Setup menu and fill the final integration time row with 10 seconds. Simulation time box in SimuLink is within reach. After running both models, the results evidently match, hence the model validation. To sum up, this tutorial demonstrates how to make a replica of a relatively complex block available in SimuLink Aerospace blockset, and, more importantly, use it for free. The xCos model might be downloaded from GitHub link in description box below. If you encounter some issues in the model, please write a message. Thank you for watching the video.